The graph partitioning problem is a fundamental problem in computer science and network analysis that aims to divide a graph into subsets of vertices. For instance, it could be used to identify groups of friends in social networks. Consider a social network where users follow each other. The goal is to find subsets of people that minimize the connections between the groups, hence maximizes the connections inside the groups. In our work, we analyze the balanced graph partitioning problem, where the graph is divided into two equal-size subsets. Let's formally define the problem. Let G be a graph with vertices V and edges E. Then, the problem aims to find two disjoint subsets of V, V1 and V2, such that union is again V, and the amount of edges that cross from V1 to V2 are minimum. The size of Vn can be assumed to be even, since a redundant vertex can always be added. In order to represent a solution of the problem, we will use binary vectors with n divided by two total coordinates with value 1. However, this representation repeats some solutions, since swapping ones and zeros gives another representation of the same solution. Therefore, the first vertex is fixed to be 0, ensuring no repetitions. The graph partitioning problem is a well-known NP-hard problem, as the size of the codification space is the number of subsets of size n divided by 2. Out of a set of size n-1, it can be proven that the codification space grows exponentially with n. Indeed, using Stirling's approximation for factorials, we get the following approximation. You can now see how the problem size increases as the number of vertices increase. Since this is an NP-hard problem, it has to be optimized with an heuristic approach. Local search algorithms do so by finding neighbor solutions of an initial solution x0 and selecting the most promising neighbor to be the x0 of the next iteration. In order to know what neighbors are, we need to define what's a neighboring system. Formally, a neighboring system is a function that takes a solution x and returns a set of solutions n of x that we call neighborhood. For example, exchanging one vertex of each partition, a process we define as one swap, generates a neighboring system. Solutions of the same neighborhood should be similar. Therefore, we propose a neighboring system that for each solution, x aims to explicitly calculate a set of solutions, n of x, with near the lowest possible differences between objective values. To do so, we define the impact factor I of a vertex v for the solution x as the amount by which the objective function f would change if only that vertex were moved from its set to the other set by allowing unbalanced sets. It can be calculated as follows. The formula adds the weights of the edges that v is connected to which are inside the set, where v is, and subtracts the weights of the edges that cross to the other set from v. Let's calculate the impact factor of vertex 1 as an example. To do so, we need to add the weights 5 and 7, since vertices 2 and 3 are connected to vertex 1 and all are in the same set. Then, we need to subtract the weight 1, since it is connected to the vertex 5 from the other set. Therefore, the impact factor of vertex 1 is 11. Notice that, if we were to move the vertex 1 to the other set, the change in the evaluation function would be 11. Once explained the impact factor, to build our similarity neighboring system, we propose to take for each set the k vertices with the lowest absolute impact factor. Then, the neighborhood is built by combining those vertices with all the possible one swap, two swaps, k swaps. We also propose the dissimilarity neighboring system, which is the same but taking the k vertices with the lowest impact factor. We propose 6 local search-based algorithms. The first 5 algorithms will consist on basic multi-start local searches, and the last algorithm will consist on the more advanced simulated annealing. Multi-start local search consists on executing local search multiple times by changing the initial solution. Different techniques to restart the local search give us different algorithms, allowing us to create a variety of algorithms easily. The first 3 algorithms, rswap, rsim, and rdissim, consist on random multi-start with one swap, similarity, and dissimilarity neighboring systems, respectively. The sim-dissim algorithm performs the local search with the dissimilarity neighboring system and performs the restart using the similarity neighboring system to generate new starting solutions. The dissim-sim algorithm does the same, but with the neighboring systems reverted. Lastly, we also implemented the simulated annealing algorithm with the one-swap neighboring system. The genetic algorithm operates on a population of binary chromosomes, each representing a potential solution to our problem. These chromosomes are evaluated based on their fitness, which aims to minimize the number of edges cut between partitions, guiding the search toward optimal solutions. The initial population is generated with 2 techniques: random initialization and Fiedler vector-based initialization. Here, half of the population is generated randomly, while the other half leverages the Fiedler vector derived from the graph's Laplacian matrix. This approach incorporates spectral graph theory insights, guiding the algorithm towards potentially high-quality solutions. Replacement strategy. After generating offspring through selection, crossover, and mutation, we need to determine how to form the next generation. We use an elitism strategy, retaining the top 5% individuals from the current generation to ensure that the quality of solutions does not degrade. Selection operator. Selection favors individuals with superior fitness, ensuring their genetic material is passed on to the next generation. We calculate selection probabilities inversely proportional to each individual's cut value, emphasizing the importance of minimizing edge cuts. These probabilities form a roulette wheel distribution, where individuals with lower cut values have a higher chance of selection. For each differing node, the crossover operator calculates an impact factor and sorts these nodes in ascending order, giving priority to those with a lower or negative impact factor. A fixed number of these nodes are then exchanged between the parents. Mutation operator. Mutation introduces random alterations to offspring, promoting genetic diversity and preventing premature convergence. In our implementation, we randomly select a set of nodes from one partition and exchange it with a set of nodes from the other partition. This process explores new regions of the solution space, enhancing the algorithm's robustness. A predefined percentage of the population receives a local refinement, using the dissimilarity neighborhood. Over successive generations, the population evolves. In each generation, crossover and mutation introduce new solutions, and the best individuals are selected to propagate their genetic information to the next generation. As generations progress, the population becomes more optimized, and we highlight the best solution when this process ends. To compare the algorithms, we randomly generated problems by creating the weight matrices for n equals 50, 100, 150, 200, and 250. For each of the 5 n values, we generated 10 different random problems, and we optimized each of the problems with all the algorithms. For every randomly generated problem, we run all algorithms and rank their performance on a scale from 0, best, to 1, worst, with this rule. Notice that multiple algorithms can share the same rank. Then, for each problem size, We compute the average rank over the 10 randomly generated problems. For n equals 50, 100, the R-DISM algorithm returns the best solution among all the algorithms in almost every problem. For bigger n values, the simulated annealing outperforms all other algorithms. However, the R-DISM is much faster than the simulated annealing and returns quite good solutions. As a conclusion, even though the insights of the neighboring systems is that neighborhoods should have similar solutions, we verified that local search algorithms perform better with the dissimilarity neighboring system rather than with the similarity neighboring system. Also, R-DISM excels at small n values, and for bigger ones returns quite good solutions that do not get far from the one given by simulated annealing. Especially, taking into consideration the execution times, the algorithm could be a good alternative for simulated annealing.